Welcome. Here's a review of the universal law of gravitation and satellite motion. According to Isaac Newton, all objects pull on each other with gravity. According to Newton, the strength of this force depends on the mass of the two objects. We're going to use big M for one of the two objects and little m for the other object. Recall that a force is an interaction between two objects. The larger the mass is, the greater the force. The strength of the force also depends on the distance between the two masses. The greater the distance, the smaller the force. So we're going to set this up as a fraction, and we're going to put the distance between them on the bottom. We're going to call it r, because when we start dealing with satellites, you'll notice that the distance between two objects is typically the radius of a circle. Now, gravity works a lot like light. So pretend this is a light bulb right here where it says S. At a certain distance r from source S, the light's spread out over so much area. But if we get twice as far away, it's spread out over an area that's twice as wide and twice as tall, giving us 4 times as much area. Same amount of light over 4 times the area means that the light is 1/4 as bright. Again, if we get 3 times as far away, it's 3 times as wide and 3 times as high, giving us 9 times the area. The same amount of light, which is right here at 1 radius, now covers 9 times the area at 3 radii. 9 times the area means that the light is 1/9 as bright. So with our distance in the denominator of this fraction, we're actually going to square it. This is known as the inverse square law. So the force is equal to the product of the masses divided by their distance squared. Small problem here. If I were to plug in numbers, I'd like to use kilograms for mass, and I'd like to use meters for radius or distance. If I do, I'm not going to get newtons for my unit of force. I'd like to get newtons. So I'm going to add a conversion factor, and that conversion factor is capital letter G, the universal gravitational constant. The universal gravitational constant is 6.67 times 10 to the negative 11th. Don't get that mixed up with lowercase g, which is 9.8 meters per second squared on the surface of the Earth. Now, if the unit for mass is the kilogram, we have 2 of them in the numerator here. This becomes kilograms squared. And in the bottom, if the unit of distance is meter, we have meters in the bottom, squared. A kilogram squared per meter squared does not equal a newton. We'd like it to equal a newton, so we're going to put some units on the end of our gravitational constant to make sure that happens. First, to get rid of kilograms squared per meter squared, we're going to put meters squared per kilogram squared. This ensures that we have no units left. We'd like newtons, so we're just going to put newtons in the beginning of that. And our universal gravitational constant is 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. Now, years earlier, Newton had told us that force equals mass times acceleration. And if that force happens to be gravity, F equals G, big M, little m, over R squared. Well, if F equals ma, and here's m, that means the rest of this must be acceleration. So we'll get rid of the m, and the force turns into acceleration. When acceleration is due to gravity, we don't call it, we don't use letter A. We use lowercase g, and that's G for gravitational acceleration. Now, if we were to plug in the numbers for Earth, it would look like this. 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times the mass of the Earth, 5.97 times 10 to the 24th kilograms divided by the radius of the Earth squared. These are all easy numbers to look up. The radius of the Earth is 6371000 meters, and this whole thing gets squared. And if we were to plug this into our calculator, we would find that the value of G equals 9.8 meters per second squared. Here we see an animation of a satellite going around the Earth. According to Newton, gravity is the force that's keeping this satellite in orbit around the Earth. Gravity is acting as a centripetal force, keeping the satellite in motion. And if we were to phrase it just like that, the centripetal force causing satellite motion is the force due to gravity, we could actually figure out how fast the satellite has to move. Recall from earlier in the year that centripetal. So if you recall from earlier in the year, the formula for centripetal force is mv squared over r. And the centripetal force keeping a satellite in orbit is the force due to gravity, which is g m little m over r squared. If you'll notice, lowercase m, that's the mass of the satellite, appears on both sides of the equal sign. Therefore, I can cancel them out. We don't need to know the mass of the satellite to figure out how fast it has to go. We'll also notice that the radius down here cancels with one of the two radii over here. Recall that r squared simply means r times r. So this radius will cancel with one of these. And when this cleans up, we have v squared equals g m over r. And of course I don't want v squared, I simply want v, so we're going to take the square root of both sides. And taking the square root of something that's squared, square root of v squared simply leaves us with v. And here's our circular orbital velocity equation. It turns out we can also calculate how long it will take the satellite to go around the Earth. We call this amount of time the satellite's period. And for period, we're going to use capital T. Earlier, we've been using lowercase t for time, but when our time is something that happens over and over again, we call it a period, and we use capital T. What's the satellite going to do once it's gone all the way around the Earth? It's going to do it again. So recall that time is distance over speed. If we take a look at our animation of a satellite going around the Earth, when it's gone all the way around the Earth once, it's completed a circumference. So the circumference of the circle is the distance. And the circumference of a circle is 2 pi times the radius of that circle. And we computed a moment ago the speed, gm over r square rooted. Gm over r square rooted. And here's our period formula. If we went straight to the calculator with this formula, we'd get the correct answer, but this can be cleaned up a bit. We have an r down here and an r up here, and that's a little sloppy. So I'd like to get rid of the root symbol. Let's start by squaring everything in the equation. And anytime we square something that's under a root symbol, it simply comes out of the root symbol. Now we have division of a fraction, which means we're going to flip this fraction upside down and multiply the top by the new fraction. And it's the same as taking this r and just moving it up 2 levels. The top becomes r cubed. And the bottom is simply gm. 2 squared pi squared r cubed over gm. This is equal to t squared. Well, I'd like to get rid of the squared now. So I'm going to square root and square root, and the square root of t squared is simply t. So squared equals 2 pi squared r cubed over gm. And since 2 is squared and pi is squared, I can pull them out of the root symbol simply as 2 pi. And here's our period formula for a satellite. Period equals 2 pi square root r cubed over gm. Now the formula that we derived for orbital speed is the speed for a perfectly circular orbit. What would happen if we went faster than this? Our satellite would travel farther from the Earth, and our orbit would become elliptical. Faster still, and the object becomes even more elliptical. Don't worry, it'll come back. But if we go fast enough, we'll reach a speed with which it never comes back. And this is known as escape velocity. And the formula for escape velocity is v, ESC for escape, equals 2gm over r. You notice that it's identical to the formula for circular orbital velocity except for the 2 up here. So escape velocity is the square root of 2 times the gravitational constant times the mass of the Earth multiplied by the distance of the Earth in meters. Let's review Kepler's laws of planetary motion. There's 3 of them. Here's a diagram of an ellipse. An ellipse is like an elongated circle. Like a circle, it has a center. But a circle has a radius, and a radius is the distance from the center to any point on the circumference of the circle. Well, in an ellipse, it's difficult to determine what we're going to use for that radius. We have 2 choices. We have the major axis and we have the minor axis. So both of these are like diameters. And we have the semi-major axis, which is the distance from the center out here to the vertex. And we have the semi-minor axis, which is the distance from the center to the circumference of the ellipse. Well, it turns out that the semi-major axis is the one we're going to use because the math is identical to the math that we would use for a circular orbit. Every ellipse has two foci. That's the plural for focus. We have a focus here and a focus here. At one focus will sit the sun, assuming this is a planet going around the sun. This could be the Earth right here, in which case this could be a satellite going around the Earth. And in the other focus sits nothing. It's just empty space. So the sun sits at a focus. Kepler's second law says that planets sweep out equal areas in equal time. Now notice in this animation of a planet going around the sun, when it's farthest from the sun, it travels quite slow, and as it gets close to the sun, it travels very fast. As it gets further from the sun, it slows down. It's no different than taking a rock and tossing it up in the air. The farther it gets from the Earth, the slower it moves, and the closer it gets to the Earth, the faster it moves. Let's watch it come in again. Watch how fast it moves. And it moves much faster when it's in here. So what Kepler's second law is telling us is that because it moves faster when it's near the sun, it's going to cover more distance. So let's say, for example, it took the planet a week to do this, to go from here to here. When it's out here and it's moving slower, it's going to take a week to do from here to here. It covers less distance. And it's going to take a week to go from here to here. It'll cover even less distance. But it's further from the sun. And so if we take some lines and connect these 2 points to the sun, and we shade in this area, and we do the same over here, we shade in this area, and we shade in this area. According to Kepler, all three of these areas will have the same area. And Kepler's third law says that the period squared is equal to the radius cubed of the orbit. This is a fancy way of saying that planets that are close to the sun take less time to orbit the sun. There's two reasons for this. Here's an animation of our solar system. Notice that the planet Mercury doesn't take very long to go around the sun compared to the planets that are farther out. It does it much faster than Venus. Venus does it faster than Earth, Earth faster than Mars, and Mars faster than Jupiter. The reason that Mercury takes less time to go around the sun is because it has a shorter distance to go and it's moving faster. This model of the universe, where all the planets go around the sun, is called the Copernicus model. Back in the days of Copernicus, only the planets out to Saturn were known. The rest need telescopes. In Copernicus's model of the solar system, the planets orbit the sun. But prior to this, people thought that everything orbited the Earth. This is known as Ptolemy's model of the universe. This is known as Ptolemy's model. This is known as Ptolemy's model of the solar system. In his name, the P is silent. In Ptolemy's model of the solar system, everything orbits the Earth. And the solar system would look like this. the solar system would look like this. Now these formulas assume that everything that's orbiting the Earth is external to the Earth. If there happened to be a giant hole drilled through the middle of the Earth and you jumped in, as you got closer to the middle, gravity would actually get weaker and weaker. And when you're in the very center of the Earth, there'd be no gravity at all. You'd still fall right through it. We're going to ignore air resistance here, but if you jumped in, you'd speed up, you'd speed up, you'd speed up, you'd be going quickest in the middle. Then you start to slow down, slow down, slow down until you came to the other side and you fall right back through again, and it'd take you a little less than an hour and a half to do a complete round trip from one part to the other. If you could happen to stop here in the middle, you'd find yourself weightless, just like astronauts in the space station.